In this video, we are going to see how we can solve the allocation problem using the Hungarian method. So if you have n resources to do n tasks, each of the resources will have a certain cost associated with it, and we have to come up with a solution or a combination such that the cost is minimum, and we can use the Hungarian method to do so. So I've taken this example where I have three workers and three jobs. So one of the possible combinations is worker 1 takes job 1, and the cost associated to do that job is 250, and I can do the same for worker 2 job 2, and that is 600. Worker 3 job 3, that's 250. So the total is going to be 250 plus 60 600 plus 250, that's 1100. But we do know there exists another combination where the cost is not 1100, but it's going to be something less than that, and the Hungarian method is a algorithm which will help you come up with that particular combination. So this is what we are going to do in this particular video. So let's go with this example. So the first step that we need to do is we need to find the smallest element in each row. So in this case, so in the first row is going to be 250. For the second row, it's going to be 350, and for the third row, it's going to be 200. Now our task is to subtract this element with each and every other element in the same row. So let's do that. Let's create another matrix, and that would be something like this. So 250 minus 250 is 0. Then it's going to be 150. Then it's going to be 100. Now we need to subtract 350 from each and every element. This is going to be 50, and this is going to be 250. This is going to be 0. This is going to be 0, 200, and 50. Right? So this is the first step that we need to carry out. So first step. Now the second step, we need to perform the same action again, but this time it's going to be column wise. So let's do that. So if I look at the first column, 0 is the smallest element, so we are going to subtract 0 from each and every other element, and it's not going to change. If you go to the second column, the smallest entry is 150, so it's going to be 0, 100, 50. For third, it's going to be the same. So this is our step 2. Let's move on to the step 3. We, we have to make lines in such a way that it's, it covers all the zeros that we have just formed. So if I look at the matrix here, so if I create a line from covering the first two zeros here, it's going to be something like this. If I do one more, it's going to be something like this, and if I do one more, it's going to be something like this, right? So I've created three lines, and each of those lines is covering the zeros that we just got by reducing the columns and the rows. Okay, so if step number 4 is if the size of the matrix is equal to the number of lines, we stop, as in we do not go further, and we have reached an optimal solution, and we just need to figure out which numbers are there from the original matrix. Okay, so in this case it does happen like that, right? So the size is 3, and which is equal to the number of lines, which is 3, right? So if you look at the matrix right now, so in each row or column there's a 0. So if I consider this 0 for this particular row and column, and this particular 0 for the second column, and this particular 0 for the third column, and if we compare this particular matrix with the original matrix, so the original matrix is this one, and the position, the circled, there's a green circles would be the ones which is the optimal combination, which is actually solving the allocation problem. All right, so let's check this. So I'll circle this 200, then it's going to be 400, and then it's going to be 350, right? So if I add all these, it's going to be 200 plus 400 plus 350, and that's going to be 950, right? So 950 is the minimum cost that is required for each of the worker to do each of the other job that they are assigned, right? So if you take any other combination other than this, it's definitely going to be more than 950, and that is not what we want, right? We want to do we want to complete all the jobs in the minimum cost. So if worker 1 takes job 2, worker 2 takes job 3, and worker 3 takes job 1, we can say that this combination is the optimal combination which will give you the minimum cost and all the jobs can be done. All right, so so these are the steps that you need to perform. So for this particular example, we had to carry out the reductions, the row, column, and drawing of the lines only once, but that is not always true. Sometimes it's going to happen that the size of the matrix is not equal to the number of lines, and then we need to carry out some other operations also. So let's look at an example where the size of the matrix is not equal to the number of lines, and we need to perform a couple of more steps to reach to the minimum cost using the Hungarian method. So I've taken this example where I have 4 workers and 4 jobs and the cost associated with it, and I've already formulated or calculated the row reduction and the column reduction. So if you see in the first row, 70 is the minimum value, and I've subtracted that with each and every other element. For the next row, it's 40, then it's 5, and then in the last row, it's 10. And after that, we have got the first matrix by performing the first step. We are going to do the same with the same step again, but this time it's going to be column wise, and that's going to be our second step. So if you look at the matrix, 7 is going to be 0 is going to be the smallest value. In the second column, it's again 0. In the third column, it's again 0. So the first 3 columns are going to be the exactly same. But in the last column, if you see 10 is the smallest value, so we are going to subtract this element with each and every other element. And this is the matrix that we get. So let me copy this matrix. So now our next task is we need to create lines in such a way that it covers all the zeros with the minimum number of lines. So if you see on the last row, we can create one line like this. There can be another line like this, and one last line covering the last zero like this. So if you see, there are 3 lines covering the zeros, and but the size of the matrix is 4. So now we need to perform additional steps to go to the minimum cost using this Hungarian method. Now what we need to do is we need to look at all the uncovered elements, and in that uncovered elements we need to find the smallest element. So within the uncovered elements you can see 7 is the smallest element. Now the next step is we need to subtract 7 with all the uncovered values. So -7 with all the uncovered values, and you need to do +7 to all the values which are covered twice. So covered values but twice. So if you look at this matrix, we'll subtract from all the uncovered elements, but we are going to add 7 to the values which are covered twice. So if you see, 90 is one of those values, and this particular 10 is one of those values. So let's do that now. So I'll create this matrix here. So this is an uncovered value, so that's going to be 3, then again 3, this is going to be 0, then again 3, 35, 0. Now this is the value which is covered twice, and we need to add, so that's 17, then 40. Now this 7 becomes 0. 65 minus 7 is 58, then 0, again 58, 0, 0. Now this is the value which is covered twice, so it's going to be 97 and then 0. So this is our new matrix which uh, is covered. So this is a new matrix with a different number of zeros. Now we perform this step again where we need to create lines. So let's change the color, and now let's create lines similarly the way we did it earlier. So it's going to be something like this, and we can have this line as well, this particular line, and this last one. So if you see now, we have 4 lines, and the size of the matrix is also 4. So this means we have reached our solution, and now we need to stop. So the next step, if you remember what we did earlier in the earlier example, now we need to come up with the values where the value is 0, but we need to compare it with the original matrix, right? So this is our original matrix. So let's see which zeros we can take. We can take this 0 for this particular row and column. We can take this particular 0 for this row and column, this particular 0 and this particular 0. So we have taken 4 zeros. Let's check the corresponding values at this position with the original matrix. So it's going to be 20, then it's 12, 40 and 70. So these are the values or combinations that the workers need to take with that respective jobs so that the cost is minimum. So let's check that now. So worker 1 is going to take job 3, the value is 70. Worker 2 goes to job 2 with value 40. Worker 3 goes to job 1 with value 12, and the last worker goes to the last job with value 20. So if you add these values, it's going to be 70 plus 40, that's 110, plus 20, that's 130, plus 12, that's 142, right? That's 142. So this is the minimum cost that is required for the workers to get the jobs done. So in this way you can solve any allocation problem with Hungarian method. So this is what I wanted to show you in this particular video. If you like our content, please like, share and subscribe. Thank you.